So I hope YouTube stream is working. Hello, and welcome back to another workshop at Kspace. I'm Lauri, and today I'm going to talk about how you can package applications for Kubernetes. So it will be sort of a mix between Docker and various different technologies. So should be also useful for people who have absolutely nothing to do with Kubernetes as well. So again, the agenda, why we're doing this, we want to get more Hackerspace members for our Hackerspace. And we're doing this with, in cooperation with Startup Estonia. The goal here is to upskill people on the Estonian market, improve the skills, security skills of tech workers, and hopefully that should also result higher salary, etc. for you as well. So at least you are here because of that, right? Okay, so first let's get some buzzwords going. Today we're going to talk about Docker, Kaniko, Scaffold, Drone. We're going to talk about different programming languages. I've prepared a couple examples using different programming languages, how you can build them with Docker and how you can deploy them into the Kubernetes cluster. The scope of this particular workshop is wide, which means that I'm not constraining this particularly to AWS EKS or self-hosted Kubernetes cluster, so it should be widely applicable in different scenarios. So that's why maybe some of the examples are maybe a bit far for people who are focused solely on EKS applications. And afterwards, we're going to get some pizza. So, Erki.
This is why I'm here.
That's why people are here, of course. Get the pizzas, right? Pizzas. So, one of the big philosophical questions that I had when I started with Kubernetes was that, what is the stuff that actually makes sense to move to containers? So I guess many of you will have sort of similar questions. And I'm going to try to give some insights. There's no absolute truth here, so you basically have to evaluate the reality based on your experience. Let me just give you my view on this topic. So I guess there's first of all, there's two broad categories. One is the applications that you are developing in-house for your organization or for your hobby purposes or whatever. And the whole other category is applications that are developed by someone else. A good example is, MySQL servers and I don't know what we run here, for example, Wiki.js. It's a wiki application. I'm not developing this. At best, I will maybe report some bugs to this project, but very likely I will not make any major modifications to the program because I'm not, I don't know, for example, me, I'm not fluent in JavaScript, so Nodejs is written in JavaScript. Probably I'm not going to make any pull request to that project to actually improve it and so forth. And I'm going to try to break down both of these scenarios here. Let's actually start off with third-party applications because that's probably, even if your end goal is to run own applications, you will still need to run something that is written by someone else, right? And I think these are some useful evaluation criteria for these applications. Does the application, for example, have Prometheus metrics endpoint? Many old-school applications don't. So, for example, just off the top of my head, I don't know, Elasticsearch, Graylog, even Nginx. These applications, they do not have Prometheus metrics endpoint. And in those cases, some third-party people have written so-called Prometheus exporters. So if you're not familiar with Prometheus metrics in general, this is a HTTP endpoint which serves some sort of numbers about the application. Most usually you will serve their counts of errors, latencies, some sort of measurable numbers that you can use in alerting or to determine what is the health of the application. So, but the point here, even if you're at the moment, maybe you're overwhelmed with all of the Kubernetes stuff, at the moment, maybe you don't even care about this, but just checking whether the application has Prometheus metrics endpoint is a good indication about whether it is a good idea to move it into Kubernetes. So yes, as I said, many old school applications do not have a Prometheus metrics endpoint. Many people, even if you raise a issue on GitHub and ask them, could you add Prometheus metrics endpoint, they do not even understand why it's important. So you might find yourself in a situation where the developer doesn't understand, doesn't care, just whatever. I think one of the memories that I have is that, for example, this software that we have for the 3D printer, I think it's called Fluid P. And I think, was it me or was it someone else who had raised the issue that, hey guys, you should add Prometheus metrics that we could monitor the printer. But they said they didn't even understand what the hell we asked, basically. And they said, yeah, you can write yourself something if you need to. But basically what I'm saying is that like a good project evaluation metric is whether the project has like a built-in Prometheus metric support, and if it doesn't, maybe they have a Prometheus exporter. So Prometheus exporter, for example, is available for MySQL, Postgres, Redis, Mongo, like all of the databases, they have Prometheus exporters, which means basically that the exporter is a piece of software that connects to the application, fetches the metrics, and then exposes them in the Prometheus format. It's just like a format converter, really. But even if the exporter is available, in many cases they do some sort of weird conversion, which again doesn't make sense. So in particular, I found very frustrating to use Mongo exporter. It just exports the Mongo metrics as is. All of them, they use abbreviations. And basically, I would have to be like Mongo database expert to understand these metrics, because they don't give you like any kind of like a top level okay metric. Is everything okay? Nobody knows. You just get like bunch of internal database internal metrics to use, which is practically useless. Another thing that you might want to look at is, does the project have Docker file? So in many projects, even if there is a Docker file, it might be the case that they are not building Docker images. So these are again the things that you might want to consider. If a project doesn't have a Docker file, then you basically need to, you assume the role of a package maintainer. So you would have to basically fork the repo, add the Docker file, and then do something with it yourself. But I guess if your aim is to host stuff on Kubernetes, you will anyway need the skill of building Docker images and hosting the Docker images. So if you're like thinking that, oh, I'm not going to build anything, I'm just going to use third-party Docker images, then practically that will be very hard to actually make happen, because you will sooner or later you will end up in a situation where you need to build a Docker image, you need to host it somewhere in order to make it available for your cluster. So like being able to build Docker images and being able to host Docker images are like two important skills, and you should definitely figure out how to do that. So even if the Docker file exists, sometimes the developers, they don't provide ready-built images. And even if they do, then you might find yourself in a situation where, for example, nowadays the ARM CPUs are very hot topic, right? So the new Macs have ARM CPUs. AWS provides these ARM workers for Kubernetes clusters or in general. And well, Raspberry Pi uses also ARM CPU. So, but in many cases, the developers are like, our enterprise customers are using x86 Intel CPUs. We don't care about your ARM. And then, then you're ending up in a situation where you either have to run x86 CPUs for some workloads, or again, need to build the images yourself. So these are some of the things to consider when when you're thinking that, I would like to migrate to Kubernetes, or even if you would want to migrate to Docker, I think most of this is applicable there as well. These are some things to help you determine whether it's a sane journey to begin with, basically. And if you're beyond these questions, then let's say if you're going to package something yourself for Kubernetes or Docker, what are the types of workloads that are actually applicable for Docker and Kubernetes? So the Kubernetes networking stack works only with TCP and UDP. There are not many protocols beyond TCP, UDP, but for example, IPsec uses a different kind of protocol, which is not TCP and not UDP. MQTT probably is based on TCP anyway. Okay. So practically speaking, anything that has something to do with web probably uses TCP anyway. UDP, why I brought in UDP here is that, let's say if you want to run a DNS server for whatever masochistic reason, I'm doing that, but that's more like a thought experiment really. Can I do it? Yes, I can. I can run a bin DNS server inside Kubernetes cluster. Just you have to keep in mind that with DNS you need to handle both TCP and UDP. And one other application that we have here in the space is we have the VoIP phones. They use Asterisk, this PBX software. I think Asterisk has something to do with UDP as well, but I haven't tried moving Asterisk yet. Sorry? With UDP, so yeah. So that's why I put here like for a thought experiment, Bind works. I suspect that Asterisk would also could be made usable on Kubernetes, but that's probably like very, very esoteric corner case that most people will not end up with. If we talk about generally, then Kubernetes, yes, I would say was designed to run web applications mainly, which implies pretty much is TCP. And that's why the ingress also has a very central part in Kubernetes, because the ingress is basically the virtual host and routing mechanism. So it's very closely coupled with that, which means web. But there is nothing that prevents you from running like arbitrary TCP application. So for example, at work last week, I migrated some SMTP components into Kubernetes. So SMTP is the email infra kind of thing, runs on port 25, or yeah, I think it's 25. Uses TLS, but has nothing to do with ingress or web. And yes, it was possible to migrate this. It works. You can get the public IP addresses assigned to these pods that need to talk to the outside world using SMTP, or actually need to get the incoming connections from SMTP, and all of that works. So that's doable, and that's not a crazy idea. So like for web for sure, but like let's say for example email, yes, for sure you can do that with Kubernetes. Just you have nothing to do with ingresses anymore. And on the other side, like IPsec, you cannot do IPsec basically, practically. And actually, well, VPN in general, that doesn't compute really. Only applicable use case maybe here is like the administrative UI of some sort of VPN solution. So then in that case, you would run the admin UI inside the Kubernetes cluster, but the actual OpenVPN would still be running somewhere on some sort of network device or some sort of firewall device, I suppose. Regarding classic web applications, yes, you can run classic web applications. There's just a couple things you might want to consider. Most PHP applications, they tend to be designed in the way that PHP, like for example, in WordPress, you have the WordPress plugins, right? And what do the plugins do? They change the files on the root file system or wherever the WordPress is installed, which means that it's changing the contents of the root file system. Then you need to figure out how to persist these changes over pod restarts, which practically means that this plugin folder, you need to probably mount it as a persistent volume, so all of the plugins will get installed there or something like that. But yeah, if you're designing applications from ground up, then you can already factor in the peculiarities of Kubernetes that, for example, you do not write to the hard disk. Actually, plugins as such do not really exist in Kubernetes. You design the application in a whole different way. Yes, I briefly showed the scary picture. So in practice, what does it mean? So like all of this discussion leaves with lots of open-ended questions, like should I do this, should I do that? I thought it's a good chance to actually demo one of the applications that we built here for the hackerspace and discuss like what's going on here. And it maybe looks a bit scary, but I'm going to try to break it down, the basics, so you would understand what's going on. So this is the application that we have here. It's our webcam application. So the point of the webcam application is that people can see remotely who is at the space and then come here to socialize. And yeah, Alexei can wave the hand there. We've tried to keep like the areas where people tend to work. These are not in the what is it, field of view of the camera. So people get to maintain their privacy when they want to, but the social gathering areas, those are visible. And of course, like the doors, so you can know, like somebody calls me that, hey Lauri, can you let me in? But then at which door you are, then you can see it from the webcams at which door the people are. And of course, we've got the server room here. So the server room has random people are not supposed to be there, so that's why it's also monitored. And also the workshop, if somebody accidentally cuts off their hands, or he's lying there on the floor, then somebody should call ambulance, right? So, and we've had actually this from the start, but the difference is that in the very beginning, I used this software with a very stupid name. It's Motion Project. It's actually the one of the most terrible names that I've found for a software project. Like, how do you find this? So the search string is useless practically. So we started off with this, but this software runs as one process. You cannot run it across multiple machines. If you start adding cameras, then eventually you will max out either one CPU, one thread, one machine, whatever. And I thought, as a thought experiment, can I just write something like this from scratch? And this is basically the architecture that we ended up with. And so yeah, we've got the cameras. These are usual, what is it called? IP cameras, or what's the industry term word? In practice, it means that there is a HTTP port that you can connect to, and you get mJPEG stream. An mJPEG stream essentially is just a bunch of concatenated JPEG frames. It's actually, I think it's not even a standard. It's like some dirty hack that somebody came up with. And I think it actually, the reason why it was adopted so broadly was that when a web browser connects to a HTTP URL, and if it outputs the JPEG frame, the browser displays it. But if you keep on outputting more frames, it actually updates what you see in the browser. I think it was sort of a hack on top of these old browsers that they managed to exploit. So it predates, like this thing predates like the video tag in HTML5. So it's just image tag where accidentally the browser keeps updating the image, what is shown in the browser. So that's how these old dumb web cameras worked. And we've got the orange camera motion detect component. This is now, let's call it, that's a microservice. All of the orange things are written in Python. So I wrote the software that is running there. It basically connects to the camera, and it tries to do the motion detection. And if it sees a motion, it actually gets recorded in the database as well, that there was a motion. I'm going to show the log in a moment. So this motion detection piece is written in Python. Very dumb piece, just something like 100 or 200 lines of Python, very basic stuff. And the reason why I use Python is because the OpenCV library that is used for image processing is available for Python. It's very easy to use from Python, for example, compared to maybe some other programming languages. And it also has listening port running on that service. And that listening port allows you to get the same frames that the motion detection software sees. And the point of this is that the only piece that connects to the camera is the motion detection software. So in order to not overwhelm the camera with incoming connections. Then you maybe notice that there's two boxes drawn here, right? So I've tried to design it in a way where you can run it in a highly available fashion. So you run two pods of the same software. Both of them, they try to perform the motion detection. Both of them, they try to insert events to the database. But the way the software is written is that so only one of them eventually ends up as effective. So I had a very lengthy discussion about this with several software architects, like, how would you do this? You could also, the alternative solution would be that between these two pods, you would elect the master, which one is the one that is writing events at the moment. But then even in that case, you might end up in a situation where some of the frames get lost and it takes some time before the other pod takes over. But this approach where you just use the Mongo upsert functionality and construct a query and insert parameters in a way that the first one that manages to execute it actually causes a new event to be added, and the second one merely like updates the timestamp or something like that. So there is no duplicate events inserted to the database, but still high availability is guaranteed for the motion detection mechanism. So this is just, this was one of the questions that I had. How do you deal with these situations where you need to, where you cannot have multiple duplicate insertions, duplicate updates, duplicate whatever happening? So this is one of the ways to achieve it. And something similar happens with the S3 endpoint. So S3, we use Minio to store the files. These are the JPEG pictures from the camera. When the motion is happening, they get uploaded to the S3 endpoint. The implementation of S3 we use is the Minio. So we run it on our own hardware. I bet you could run this whole thing in AWS as well, but it would be ridiculously expensive to run it on AWS because you would probably spend a lot of money just transferring the bytes back and forth, and then storing the bytes, and then reading the bytes and writing the bytes. But in an on-prem scenario, this actually becomes kind of reasonable from that point of view. But as I said, the upload functionality is also deduplicated, and the way it works is that it calculates like the hash of the JPEG frame. So of course, both of the motion detection pods will get exactly the same frames. If you get different frames, then something is really wrong, because it's still binary data. There's there's no way that two pods are seeing different frames. And both of them, they try to upload the frame to the S3 endpoint. And I think what actually happens in practice is that the data might get uploaded twice, but it ends up as one key. And there is no partial data written because that's how S3 works. The whole thing gets uploaded or nothing gets uploaded. So S3 solves that issue. And that's actually also one of the reasons why people are using S3, because it actually avoids a lot of the issues of classical file systems. So in a classical setup, you would do something like, oh, I have a folder in var lib pictures, I will write there. But then you have to deal with this all sorts of all of these file system related issues, like what happens with partial writes. Then you have to write it with a temporary file name, rename it to the final file name, and then you have to deal with all of this bullshit, which maybe I think it's not even your business. Like you're supposed to be writing the well, in this particular scenario, you would be writing the surveillance software, right? Not dealing with file systems. So why are you dealing with file systems? So S3 solves that issue, that you don't have to deal with the semantics of the file system, which are, by the way, different among different file systems. Like all file systems do not behave the same way. Any questions so far? Docker. I'm going to first try to show the big picture, and then let's dive into details. So as I said, the orange pieces are written in Python, because image processing in Python is easy, and talking to Mongo is easy, and talking to Minio was also relatively easy. The camera tiler is the thing that stitches this big picture together that I showed you. It pulls all of the camera streams together and then pastes it together. This is also written in Python. And the other part that I wanted to show you is this thing. So that's the motion detection, or let's say the event viewer portion. You can click here. You can see the actual frames from S3. It pulls the actual frames from the S3. And that part actually is implemented in Node.js. I didn't touch any of this. That was mostly written by Erkki. And that consists of, first of all, this, I think it was React.
Vue, actually.
Sorry, my bad. Like this. So this is a Vue front end, which is, okay, yes, to be precise, the yellow one is Nginx container that contains the Vue assets that are compiled with npm, npm build or something like that. So there is no Node.js in the yellow box. It's just Nginx with HTML, JavaScript, CSS files generated by npm. And the blue ones are the actual Node components. First of all, we got this event source component, which is actually just a generic piece to get events from Mongo. And what it does, it dumps the last X events, and then it streams the updates on top of it as well. So it registers to this Mongo watch mechanism and gets additional updates from the server as well. And all of this is served as it's a web standard called server sent events, or server sent events. So it's basically like it's like a big HTTP download that never ends, and it just streams the events in JSON format, basically. And the other component here is now the application-specific thing, which basically enriches these log records with additional pieces, which consist mainly the addresses of images, and because of S3, these are actually digitally signed addresses of images. So you cannot publicly get the images. You actually need to have a digitally signed URL, which is valid for 15 minutes or something like that. And this actually now hooks back to what I was talking about previously. How do you implement plugins in a microservice world? So obviously you don't want to, it would be a bad idea to write very application-specific components. So this log mower event source, we use it elsewhere as well. We have, for example, if you remember, in one of the very first in the very first workshops, I showed this one. So this is these are the Kubernetes pod logs. But if you look closely, the web UI is the same. So it is exactly the same. I think it's even the same Docker image. It is. Yes, it is the same Docker image. But you see how wildly different applications this component is serving. And this is now where this event broker comes into the picture. This is the one that adds the metadata. Yep.
Quick notice, the actual standard name for the event endpoint is event source.
Event source.
Yeah.
There's lots of buzz, generally speaking. I think the very broad category what we're touching here is event sourcing. And that's like the umbrella term. And under this, you've got Kafka and KubeMQ and RabbitMQ, and it's like a whole world on its own. I don't want to go there because I do not fully understand all of the different use cases. And And we could probably talk about hours, like which application is best for which use case. And that's actually maybe a good thing to remember here is that, should I use RabbitMQ for application? Depends. I have to look at the particular use cases. RabbitMQ has its own use cases, KubeMQ has its use cases, Kafka has lots of use cases, etc. But these are all for slightly different applications. And but yeah, generally speaking, the big umbrella here is the event sourcing. So in our case here, we have made this really poor man's solution for event sourcing. We just listen in Mongo and transmit them to the browser. Probably, if you would dig deeper, we could maybe use KubeMQ here to transfer the events to the browser, but I don't know enough about that. And this is just one of the possible ways to do this when you're familiar with Mongo and S3. That you maybe want to just omit the complexity of running a message queue system and use Mongo Watch instead. But Mongo Watch has, at the same time, has lots of limitations. And for example, you cannot have thousands of listeners connected to the Mongo like this. And that's where you would probably have to switch to some other technology as well. So yes, this was like totally, nothing to do with hipster startup that runs only on AWS EKS and has lots of connections to actual physical hardware, which maybe is not applicable in AWS. But I thought this was like a interesting scenario to demonstrate and also elaborate a little bit about how would you go about designing the software if you would have to break it down into components. That we don't have plugins as such. The way this event source talks to the event broker is that for every event that it gets from Mongo, it requests the event broker, please give me the images for this event. And then it renders like a chunk of HTML or something like that. A JSON array, okay. Yeah. Oh, yeah.
But the speed of this communication between those two is, for me, it was astonishing. I mean, you don't notice that a lot of like HTTP requests are made inside Kubernetes cluster. It is quite like snappy and fast, I'd say.
Mm-hmm. Just to demonstrate, I think we can actually access this, what is it, events?
Yeah, basically.
Okay.
But there are extra parameters, so you
okay.
can't.
But on this one, that's the event source, yes.
The thing is, you gotta send filters back or
okay.
like URL parameters. That's why it doesn't just stream.
But anyway, yes. It looks something like that. You just get actual JSON data with the contents inside. So the other aspect, what I would like to emphasize is that there are different programming languages in this application. So in a classic web application, you may be, we do everything with Django, that's it. But one of the aspects, or maybe what's a better example, we do everything with WordPress. But this is like completely opposite. That you use the tool that is fit for the purpose. So image processing, C++, Python are good candidates. Okay, let's do all image processing related stuff in Python or C++. Node.js is really good for event handling, like event-driven applications. Okay, let's use Node.js for these components. And with Kubernetes, it's really nice that you can mix and match and put them together. Let me quickly show you this. So all of the manifests for the camera application are in this public repo. And I just wanted to show you this ingress for the application. So the cam.kspace.ee hostname serves, of course, it's password protected. It's not publicly visible. So you need to have a Hackerspace user account to actually access this, of course. That is actually covered by this SSO middleware here. For authentication in general, I guess the extra mile here would be to use OpenID Connect, but we were lazy. We didn't want to do any fancy authentication. It's just basically everyone who has a Hackerspace user account can access this site. And the other aspect here is that the way these different microservices are tied together is using this path prefix routing. So /tiled gets routed to the camera tiler component. /m is some sort of legacy address, which also goes to camera tiler. /events goes to the event source, and everything else goes to the front end. So all of the JavaScript and CSS and all the stuff comes from there. And this is how you put like application together from different microservices, different programming languages, and so forth. So yeah, all of the application is here. I think it's one of the biggest applications that we have. So that's why I also wanted to show this. And I think nothing like this really exists in the wild. The closest one that I found was, what was it called? What's the three-headed dog? Yes. So that was the, somewhere I came across this. This was the closest that I found. But I think it still doesn't follow the microservice architecture that much. But it is like designed for cloud. And it's split up into different components as well. So that was like one of the closest pieces that I found recently. Anyway, any questions so far? So I hope this like puts some stuff in perspective that otherwise I found it really annoying that the people were talking about let's do microservices, but like how do you put this together? How do you structure the application? So this is just like one good example where it's maybe like fairly complex. Also, it's not very traditional web application either. Okay, so how would you now, let's say you figured out how you chop up your application, how do you actually get from source code into the images? So for this, we've got a Docker file. And generally speaking, I guess maybe we should talk a little bit about Docker as well. So everybody has, I suppose everybody has used Docker, right? Everybody has used Docker. But the thing is that Docker, what is Docker actually? I would like to split it into couple like distinct features and aspects. One aspect is the container runtime, that you can run containers on a machine. I think that was like probably the first and most important aspect. So when you want to run containers on your laptop, you will probably use that aspect as well. But in case of Kubernetes, that's not really. It used to be a thing that even now, some of the Kubernetes clusters in AWS, they use Docker as the runtime, which means that there is Docker daemon installed on the worker of the Kubernetes cluster, and they use the Docker to run the containers. But nowadays, there's actually a couple other alternatives, and the Kubernetes is actually slowly phasing out Docker as the container runtime. So we've got this CRIO and containerd and whatever. I don't know. I tried to dig deeper this weekend, but I still don't fully understand what is the difference between containerd and CRIO. But that's like a whole other discussion. In practice, what I'm saying is that if you're building a Kubernetes cluster nowadays, you probably don't want to use Docker as the container runtime for the cluster, because Docker daemon has quite big attack surface through this Docker socket. The other aspect about Docker, I suppose, is the Docker image format. So let's see, maybe I can do some demo even. So when you do some Docker save nginx, I think, for example, yes, nginx tar. Okay, I think I need to pull it as well. So this is the moment where Docker image layers are downloaded from the Docker registry. So this became known as the OCI standard, this Open Container Initiative or whatever. So I would say like this is one of the important aspects that grew out of Docker, the standardized format for shipping the container images and the layers of the image. And you see this Nginx container actually consists of multiple layers, and when you do docker save, it should dump it to a tarball where you can examine it. So these are the layers of the Docker image, and every layer is actually another tarball. So there's a meta info inside here, and we can actually look inside the layers as well. So I suppose user bin, this might be the lower layer. Let's look into the other layers. Oh, this is something else. Something else. User bin. So this looks like, you know what this is. This is the, it's probably the Alpine Linux root file system, contains all of your shell utilities, so you can look into the container. There is no Nginx here, so maybe we get lucky with the next layer. I mean, I'm doing this for the first time as well. Nope, it's not here. Maybe it was in the first one, actually. Could also look into the manifest. Ah, it's here. So it's in one of the layers in user bin Nginx. So that was one of the things that came out of Docker, a standardized format for distributing the Docker images and layers. And what else are we left with? Docker Hub. Well, that's not strictly maybe part of Docker software, but it's very important part of the Docker ecosystem. And I suppose that's actually the place that they will be making most of the money in the future, I suppose. And what else? I forgot something. Right, Dockerfile. So, and Dockerfile is, I would say, is just language for describing the steps for building a Docker image. But you can easily build something that is equivalent. It just needs to produce the Docker image, which contains layers in the same format. But I would say nowadays the Dockerfile is probably the industry standard way of shipping or building applications. And the Docker Hub has lots of images. I mean, I think it's insane amount of stuff that is actually pushed into Docker Hub. And maybe just to filter out from the noise, what are the things that you would be looking for? If you want to ship your application, what is it running nowadays? Maybe on Ubuntu, maybe on Red Hat, CentOS, or something like that. You can use all of these distros as the base image to ship an application. So you can do from Ubuntu and do apt-get install and place your application inside the Docker image. In this particular example, I'm gonna try to explain it after a few more bullet points. But this is like a complete example for building a image for a Python application. And the Python call on Alpine in this case uses the official Python image from Docker Hub. So Docker Hub, let's see, Docker Hub. And you will see this pattern with lots of other images as well. And let's try to look at this. I suppose that simple tags. I wouldn't say it's simple tags. Let's try to decipher like what the hell is going on here. So the Python image is based on some other OS image, because Python itself, you cannot just run Python. Python will be built on top of some sort of likely a Linux distribution, although there is Windows here as well. I'm not sure. I'm not even sure what this Windows Server core means. I think Microsoft is actually building Windows based on Linux nowadays, right? No? Azure. But is it Linux based? No. Don't know. Classified. I don't know enough about that. I'm going to try to explain everything else here. So in a normal world, you would run Python applications based on some sort of Linux distribution, and the Python provides different versions of the Python which are built on top of some other existing Linux distribution. So Bullseye is the release name for one of the Debians, Debian Linuxes. Buster is also a Debian release. Slim, I think, is like a thinner version of the official one. Maybe they removed, I don't know, manual pages or something like that. I don't know. Don't know exactly the details. We've got also Alpine. Alpine is an interesting Linux distribution because I have never used it on actual hardware, like you know, to install it from a CD or USB stick or something like that. Alpine Linux is essentially a stripped down version of Linux that doesn't contain, you know, man pages, documentation, source code, etc. You just get binaries, stuff that you can run. That's it. Everything else is deleted. So that's why Alpine exists. Is they provide like very, very small binaries for everything. They try to keep it more up to date compared to, for example, I don't know, Ubuntu. And that's why you have the Alpine tags here. So these are Python releases built on top of Alpine Linux. Likely it will just do apk add Python and use the Alpine Python package. In some other cases, you might actually have the application itself built from source code for that Docker image, but in many cases it just runs you know, from Alpine, run apk add Python, and that's it.
By the way,
Yeah.
this Windows thing is actually containerized Windows, and it must run on Windows. It's actually Windows kernel stuff.
Okay, so it's based on Windows kernel.
Yeah, it's
Okay.
literally Windows totally. Just
Okay.
Docker,
I don't know anyone who is using this. I don't know what's the business case here.
feel like normal people.
I'm running Python on Windows. By the way, if you're running Docker on Mac, it will actually run Ubuntu virtual machine on the Mac. So when you do Docker run on a Mac machine, it actually spins up a Linux VM behind the scenes. On Windows, I'm not sure what's the same. Okay.
But what if you use non-trivial, not like standard Docker, but something different?
What is something different?
Like Docker-D, for example.
I don't know. You're in some very esoteric corner case again, where likely you will get not very good support. So generally speaking, like, I think Ubuntu is very well supported Docker host operating system, as well as what you would put inside the container. But in practice, what it means having Ubuntu inside the container is just you're using like GCC and, you know, shell utilities from that operating system, because the kernel would be still the one that is from the host machine. So, I mean, like, let's say if you run Ubuntu containers on a Red Hat host, you would use the Red Hat provided Linux kernel, and the Ubuntu programs would be talking to the Red Hat provided kernel still. But the reason why it works is that Linux, what Linux did well was that it formalized the API between user space and kernel space. So actually, the differences across different Linux distributions when it comes to talking to the kernel, the differences are actually minimal, especially when it comes to applications like these, which have really nothing to do with, you know, talking to hardware. It's just you do a network on one side and they do disk I/O on the other side, basically. I mean, that's what most of the containers do, and that is very well formalized and hasn't changed really at all for a long time. So this should explain like what is Alpine and why do we have Alpine. It becomes more self-evident once you actually start building something, because in practice it means that if you use Ubuntu as a base image, you will end up something like a Docker image, which is like gigabyte. And compared to Alpine, where you will end up with a Docker image that is maybe tens of megabytes, or I mean less than 100. Depends what you do, but you know, in the order of magnitude of tens and hundreds of megabytes. The other thing that I would like to point out here is the Docker layer caching. So basically all of the statements in Docker file result in a new image layer being created. And for example, in this particular scenario, the moment I have installed GCC make and git, it produces a new Docker image layer, and when I run the pip wheel, it basically uses the existing layer to add on top of that. So all of the run statements, they get basically cached by the Docker runtime. Here now, what makes this particular example maybe a bit more confusing is that I also use multiple stages to build an image. So I've split it up into the build stage, which actually might produce some sort of, which will have, for example, the source code of, I think you will have here like the source code of some library downloaded, compiled, and installed to run the Python application. Because that's what pip does. For some of the applications, it might need to compile some sort of C libraries, and that's what happens for Sonic. It uses this libuv event management something, and then it compiles something, and that's why it needs GCC. But the point is that we don't need any of this in the final image. I just need Sonic that works and all of the binaries of the libraries that Sonic needs to function. Sonic, by the way, is a nice web framework in Python. And this as build is the way that is used to label the stages of the build. So these two instructions get saved as the build stage, and you can refer to it from the other stages. And this copy from is used to copy the binaries from this step, leaving back all of this temporary build files and whatever, source code, all the garbage gets left behind basically. And in order to copy the binary stuff in Python, pip has this wheel function or method or whatever you want to call it. Pip wheel is the command that produces Python binaries, as much as you can call Python a binary. But it's just basically, let's call them like package files. That I think in Python you can still have this compiled bytecode, this PYC files. So the wheel files contain only the compiled bytecode, leaving back the actual source code. So it will save some space on the disk again. So I would be copying these wheel files to the final image, install them, remove the wheel files, and would add my application source code to the image. Did this make sense? Yes. So it's like, in a way, it's like being obsessed how much you can shave down the image size. So if you use the image layer caching, if you use multiple stage builds, and one more thing that I didn't explain here, I use this Python unbuffered. This is some sort of weird Python and Docker interaction. When you do print statement in Python, it has some sort of weird buffering enabled by default. And you can start the application and you get no output in Docker run. It's waiting for this 4 kilobytes to fill up in the buffer or whatever. And in order to get actual line-by-line output, then you need to disable this buffering. I think this has something to do with some TTY magic and whatever, I don't know. Christian can explain that someday. I mean, you will understand it when you need to explain it, right? You know, there's pseudo TTUs and whatever weird legacy Unix stuff. Anyway, actually regarding multi-stage builds, one of the demos that I prepared for today was a Java demo. So the original guy who I asked to create a Java example, he ended up in the rabbit hole of trying to configure GitHub Actions pipeline to build the darn Docker image. But the point was that he was trying to invoke all of these Java steps directly inside GitHub Actions somehow. It was really weird. So he spent 2 days doing this, and then he gave up. And when asked, can you just give me a Docker file? He says, I don't have time anymore. So what's my point here? Don't waste your time fiddling with these CI, vendor-specific CI tools to build the images. Docker file, you can move it between, you can use it in GitHub Actions, you can use it in GitLab, you can use it anywhere. It will work anywhere because Docker file support is so prevalent, it's everywhere. As opposed to, like, let's say, even if you had gotten this GitHub Actions pipeline running, how do I run it in Drone? How do I run it in GitLab? All of these tooling are completely different, and this pipeline would not be movable between CI solutions. So Docker file in that sense is universal. You can have your, for Java applications, you would have from GDK, install OpenGDK, run the compiler, copy the jar files into the final stage, and in the final stage you would have only like OpenJRE and use the runtime only for the final stage. And all the build stuff would get left behind. Yeah.
It might be also there might be one catch with this CI/CD provider, because even if you build everything in one Docker file, usually you need to enable somehow support Docker build in CI/CD provider. Sometimes it's also get tricky because first you need to know how to do it, and second,
And that's
analyzing this build provider might take like 2 minutes, and it's crazy. Like you build this 15 seconds, but you wait 2 minutes for your place in the queue.
yeah, these are, okay, let me try to elaborate. Good points. So first one was that does your CI provider actually support Docker file, or like, being able to build stuff with the Docker? That's a good one, because running Docker inside running Docker inside Docker, it has interesting issues like related to networking, lower MTUs, packets getting lost. I've seen all sorts of weird stuff. So, the TLDR here is that use Kaniko. Kaniko doesn't actually run the Docker daemon itself. Kaniko basically is like a Docker file interpreter. It reads the Docker file, it will run the commands, that's it. It skips all the bullshit, basically. It skips all the Docker socket mess, all of the network mess, all of the spinning containers up inside containers, all of that goes away. It just takes the Docker file and runs the commands from the Docker file, and that's it. So Kaniko simplifies this quite a bit. The other thing you said was having to wait in the queue for a CI solution. Yes, that's what happens if you use SaaS, especially free. But even if you pay, I suppose they do not have infinite resources, and if there's demand, then your job might be waiting in the queue before it actually gets executed. But the thing is that if you run a Kubernetes cluster anyway, you can build stuff on that Kubernetes cluster. So that's why I wanted to show you Drone today. Drone is a CI solution that runs on Kubernetes itself. Any more questions so far? But these are two good points. Yes. But of course, like keeping the CI system running, I think I've spent keeping the Drone running. I've spent numerous days figuring out some weird stuff. But I would say life got much easier once I switched to Kaniko. Before that, it was really painful to run this Docker inside Docker. So yes, to sort of wrap up this, you might not care in the beginning again, but later you might want to minimize the Docker image size, and the size can change significantly based on which base image you use. Like switching from Ubuntu to Alpine goes from gigabyte to 100 megabytes maybe. And but there's more aspects to here as well. I'm going to show later some other Docker files as well. And yeah, the standard output behavior in Docker is kind of weird. That's why I had this Python unbuffered here. Let's see. I've already spent an hour. Let's cover this one first, and then I guess let's do something hands-on as well. And The monitoring stuff, I will actually leave monitoring like for a whole other session because the monitoring stuff can wait a bit. So, and let's say now you have managed to figure out the Docker file. There's more stuff to consider here as well. So one of the problems that I see, for example, with Flask, Flask has this issue, for example, and many other like old school web frameworks. They assume that they are running under some sort of this, what is called? Yes, they run under some sort of process management software. So like notable examples are like this Gunicorn. This is used by Python applications. Supervisor D is something similar, but I think Supervisor D is like a generic. It's for different programming languages. I think Supervisor D you would use for PHP, Python, probably Ruby as well. Something that has this FPM CGI interface or whatever. But the problem is that this doesn't really fit the way Kubernetes works. So the Supervisor D wants to keep a pool of processes, and if a process is not responsive, it will kill it. If it starts, I don't know, timing out, it will restart it, whatever. If the process itself crashes, for example, if you manage to, I don't know, invoke some sort of bug in the program that it crashes, then the point of the Supervisor D is that it restarts the process, etc. And the other aspect here is that I think it will also enable some sort of scaling. Like let's say if you have 10 PHP worker processes and all of them are busy, then it will start more processes to handle the incoming requests. But all of this is confined to one machine, right? One machine where the program runs. And if you want to leverage like multiple machines like we do in Kubernetes, then all of this breaks down. It doesn't make any sense. And I would say the recommended way to run an application in Kubernetes is that you get rid of all of this process management nonsense because it doesn't make sense in Kubernetes. Just make it simpler for yourself that you have a single process and the ingress will do the load balancing between the pods anyway. So if you have more load, you just add more pods, which get distributed across multiple machines anyway, and the ingress will do load balancing between these pods. So in practice, it means that, for example, the Sonic framework that I use, this actually supports just running one process. It uses the event loop to handle multiple connections anyway. And if you need more power, you just crank up the replicas number on for the Kubernetes deployment. But for example, Flask says specifically that, whoa, you're not running under Supervisor D. This is some development environment. I'm very scared. This is not production. This is not production grade. But in practice, this just means that the web framework developers are like, you know, it's old school project. So it will probably take some time until they realize that, okay, it might be okay to run Flask directly without Supervisor D as well. But they will have these ugly warnings there that, you know, you're supposed to run Flask under Supervisor D or some sort of process manager to make it production ready. But actually, it's just to handle these corner cases where the process dies or needs to get restarted or whatever, which is handled by Kubernetes anyway. So in Kubernetes setup, it actually makes sense to run the Python application without any Supervisor D or Gunicorn or whatever. Let me try to briefly, very quickly explain these resource requests and limits as well. So let me try to show an example maybe. Let me see if I have somewhere. Where there is a good example. Lots of stuff. Okay, let me pick something from here. This is the wrong one actually. Okay, here. So this is whatever some sort of stateful set has a container, some sort of Docker image from Docker Hub, and we have this resources section here. So there's, for every pod, basically, you can describe the CPU limit and memory limit. And in practice, what it means, first of all, I think it's worth mentioning is that you should set something. Otherwise, if you don't set these numbers, it will just use the host numbers. Let's say your host has like 24 cores, and then this pod is actually permitted to use all of the pods on that worker. And same goes for memory, that when the pod looks at how much memory this machine has, it will see 32 gigs in the host, and I'm gonna start using this 32 gigs. And the problem becomes evident when you look at Go and JVM are good examples here. So if you don't set these limits, Go will assume that the maximum number of threads that it can start up is equal to the cores on the CPU. So it might max out. It might use all of the CPUs on the host. So I would say it's reasonable to set the limit to say, I don't know, two or four cores, something that makes sense, something that is not infinity. And for example, for Go programs, you probably want to set the Go max procs to the same value. But I think then it should auto-detect it as the same one. So this will sort of limit the blast radius of what can go wrong. With JVM, I think it's a bit more interesting scenario here, because if you don't set the RAM limit for a pod, the way that most of the Java applications are configured, like for example, Elasticsearch. Elasticsearch, the way Elasticsearch works is that it will check how much memory is allocated to the container, which again, if you do not specify the limit, is the number that the host has, let's say 32 gigs. And then what the Elasticsearch startup init script does is that it will assume that half of this we can use for the application, and the other half we can should be left for the this VFS cache, the file system cache. And the problem is, the other half, it will use all of that, because that's the way JVM works. JVM doesn't release memory back to the host operating system, so whatever happens inside the Java application's memory, it will just use up all of this space. It's this dash x max or whatever it is. So basically, when you do psaux and grep for this x max or xmx, this is the number that is can be used by the application, and it will grow very well. Yes?
So, but maybe it's only case in Kaspace, because for instance in AWS, when you're choosing some machines, you like mini, 2, small, and it's already limited your.
But the problem is that then, the question here was that if you use smaller instances for the workers, isn't that a problem? But the problem is that multiple applications can still get scheduled on the same host. And let's say if you have 2 Java applications scheduled on the same host, they will be like competing for the same amount of memory. And if both of them start using memory, one of them gets killed. So
Amazon wants you to run more instances.
yes, of course they want.
One processor per one instance.
But this is just something to keep in mind, that there is no universal mapping between like how much resources you give to the container versus how much the application uses. And the thing with the memory limit is that if the application exceeds the limit, it gets killed by Kubernetes actually. Or actually, well, the Linux kernel will kill it. Kubernetes just puts the limit that this pod can have 2 gigs of memory. If it grows beyond that, it gets killed. But that's why you should set the limit. But also, the application inside the pod should correctly read the limit. And for example, what I described earlier, that half gets assigned to the application, this is the property of the Elasticsearch entry point, Docker file entry point. It has some sort of calculation script there that, how much memory gets allocated to the application. And it's the same thing with the Go, that, how many CPU cores you're going to give. What's worth mentioning here is that, as I said, if you exceed the memory limit, the pod gets killed. But if you exceed the CPU limit, you get throttled. Linux kernel artificially slows down the application. Your application gets less CPU timeshares. And I think the docs somewhere said that basically it slices up to like 5 millisecond slots, and then you start losing these 5 millisecond slots if your program uses too many CPU cycles. And now all of these limits is distinct from requests. The requests are numbers that the Kubernetes scheduler uses as the input to place the pods on the workers. So the TLDR for Java applications is that the limit should be equal to the request, because whatever you give to Java, it will use it up anyway, always. So the Kubernetes should use this as a scheduling constraint as well. For normal applications that do not grow arbitrarily, you would set the request to the minimum baseline. Let's say your application hovers somewhere 200 and 500 megabytes. Then you would set it to 200 megabytes. That this is the scheduling number. Use this number to figure out where to place it. Of course, you should have some sort of free capacity also across the whole cluster. But the point is that this is the resource that is used always by the pod. So use this as the scheduling, to play Tetris, basically. And same goes for the CPU, because you don't wanna. If you use up all the CPU cycles on the machine, then something will start slowing down. So the CPU requests should also reflect the reality. And sometimes you should adjust them, and it kind of gets annoying. And then you got some fancy automation to update the resource limits, and then it goes to hell. Anyway, this is something that, you want to, you need to strike a good balance between how much you do. But it depends on the programming language as well. So I guess enough theory. Let's look at some Docker files. Let me just go through the Docker files quickly, and then maybe we can run something as well. So it's again in the same familiar dashboard. If you haven't logged in here yet, or if you, I think I sent invites again to some people who hadn't accepted the invites as well. So if you cannot access this, then ask. Is Erki checking the YouTube channel? Yes. Is everything okay? Voice is working? Voice is working. Okay. So if you have trouble accessing the dashboard, then ping me on the YouTube, or ping me. Don't call me at the moment, but And I added here the link to these template repositories. So it's under the developing tab. By the way, I also added this database instructions here as well. So this is what we covered in this persistent workloads workshop. I added these nice tabs. You can see what databases you have, how to instantiate a new one. So we've got MySQL, Postgres, S3, and Redis covered here. And do not use the dedicated ones unless you have a good reason to. Sorry, not here. I meant in MySQL. Do not use the dedicated ones, because that would create a new cluster. Use the shared one, because that saves some space in the cluster. And you still get what you need. You just want to have a database where you can put stuff, right? So under the developing tab, there is this template repositories link. And this goes to the hard work that we did over the past evenings with Erki and with the Rust community, and with and Holger as well. They helped me to create these template Git repositories for different programming languages. So I initially had them named by the programming languages, but then I realized that it doesn't make sense because in one programming language you can have multiple frameworks. So the Node.js examples that we have here, this is like a rather vanilla Node.js example. That's actually the one that Erkki Aas used in one of the previous workshops. But then he improved on top of this and added also an Express.js based example. So this is your Express.js based hello world, consists of one JavaScript file. He added the Prometheus metrics middleware here as well. Otherwise, just returns with hello world. And I think the most interesting stuff is actually what is happening around here. So we have the scaffold stuff, which he demoed last time, but let's see in the Docker file this time. So how is this Node.js or Express.js image built? So he uses the long-term support Alpine-based Node release as the base for this is actually the development server. And for production image, he uses LTS version of the Alpine-based Node. And it just basically copies the package files, installs the dependencies, and then eventually copies the application itself. The benefit of this, again, is that the dependencies get cached here. And when you change the code, it doesn't install the dependencies again and again and again, which is really annoying. But these become much more annoying in other programming languages. So Node.js you already saw, yeah?
Can you elaborate more about cache? Because I didn't get
So elaborate more about cache. So,
the cache dependency. How to
so the point here is that you first copy the package JSON, which contains the listing of the dependencies. And when you do npm install here, it will download and install the dependencies, but not the actual application that we are writing, right? But the point is that Docker will cache everything that happened before this, unless you change these files. So unless you actually change the dependencies, all of this is still cached.
Can you show how it looks like a Docker file with uncached dependency?
You would just put the latest row.
Yeah, so you would have the npm install on the bottom, and you do not do explicit copying. You mean you're just asking how would you write it without caching?
Yeah.
You can also run whatever docker build -- no cache. But the point is that you remove the explicit ones here.
And move the copy to the
Yeah.
There was a rule like the last rows are last cached, something like that.
Yeah, I mean, it keeps the order. So basically, because if you have a copy statement here, what the copy does actually, it checks, has this file changed? If this file has changed, then all of this is invalid. Everything that comes afterward is invalid. But likely you are not changing the dependencies all the time. You're just changing the application itself. So everything else that happens before that will get cached. So what else do we have? So my very last one that I added was the Rust example. So Rust has a Rocket Web framework. Let's see. Stripped it down to basics. Lots of weird syntax that I had never seen before, but it works. I also added the Prometheus metrics endpoint, so you have /metrics that responds to Prometheus as well. And the Docker file was kind of a challenge to write because I couldn't find like a complete example for this. Let's try to see what's going on here. So again, we're using the official Rust image from Docker Hub, use it as a build stage. Here I do some old school Linux voodoo. This enables static linking of the binary. Static linking means that the compiler produces just one file that is executable. No libraries are left in the file system. This is sort of a hack. This just initializes a blank Rust project. I think this sort of does the apt-get update equivalent, that it updates the Rust package lists. Then we copy the dependencies listing again. This cargo toml is like the packages JSON. I mean, all of the languages, they're the same. Like there's nothing unique about any language really. And cargo fetch installs the dependencies. So it will download, compile, and install the dependencies. Sorry, I lied. Cargo fetch downloads the dependencies, and cargo build at this point will build the dependencies and install the dependencies. Then I actually copy the source file. This is the thing that I'm changing. So again, everything else gets cached if I do not change this cargo toml, which means that if I don't change the dependencies. And after copying the main RS, it will build again. So it will see that main RS has changed, and it will build the actual application. So this will result in the binary placed somewhere in this build image. And because I use these static linking flags, it doesn't depend anymore on the libc or whatever libraries were used to compile this binary. Usually you would have compiler linking with a dynamic linker, which means that your program is small, but it refers like, in Windows world, the DLL files. It will need some other files to function. In Linux, these are called shared object files, so .so files. But static linking enables you to produce single binary that has everything that is self-contained. So it has some benefits, but it also has some drawbacks as well. And in Docker, we have this nice construct from scratch. This gives you just blank image, nothing inside, empty image. And I copy the Rocket had some sort of config file where you can specify which IP address it listens to. So I needed to add this and specify where the config file is. And from the build stage, I just copy this single binary that does everything that I need. And basically, you end up with, well, let me show you. The whole reason why I'm doing this. So I have actually compiled it already. What the heck? So that was Hello Rocket. The image size is less than 4 megabytes, which is nearly impossible to achieve with Python or any other language, really. And that is simply because it's a statically linked binary. Of course, if you would have more complex application, you might have images inside there or something like that, but still you can skip all of the complexity of a whole full-blown operating system. And I guess this is a good chance to compare it with, I don't know, let's look at the, Python example is actually 25 megabytes is the image size, which is good enough actually. I'm going to show that how it's built in a moment. And Node.js is 300 megabytes. But again, this is Alpine based as well. Yeah?
No, I made a mistake that this is Debian based. Alpine based is 50 megabytes.
Okay, yes.
I just discovered it today morning when you started comparing these, and I was like, is it really that bad? But,
no, I'm not ranting about Node.js. I'm just demonstrating that the base image that you use to ship the binary affects the outcome a lot. And yeah, Debian puts lots of stuff inside. Alpine has, as you said, Alpine-based one would be 50 megabytes. Okay, let's look at the other languages as well. So, Go, yes, I have Go. I tried to do all the languages because I was kind of curious to see, what can I put here? What actually makes sense? So Go example, I use the Gin framework. Again, hooks up the Prometheus metrics here, responds to one URL, listens on a port, that's it. With Go, we can do something similar. that again, we have the build stage. Again, implement caching here properly, copy the dependency listings, download the dependencies, and I think this will also compile them, maybe, I'm not sure. And copy the source code, compile the source code, again, this linking voodoo to produce a static binary, and again, use the from scratch to create the empty image, just copy the binary from the previous stage and run it with whatever release flags. This resulted in, let's see, well, this was 9 megabytes. I don't know. I mean, it's still nice, right? And but I guess the main point here is that this perfectly fits the container world. The container just contains your application, not the full-blown operating system.
Unless it's a Java application.
Let's see a Java application. So I initially tried to adopt this JHipster, but then I just gave up. It was so weird. It's just, what the hell. It first installed Maven, and then it used Maven to run npm, and then it used npm to run Docker. Like there was no Docker file there. It was just npm build Docker. Somehow they used npm to build the Docker image for this. I don't know. I just gave up. It was so nonsense, and I got a bit pissed off at that they put the effort into writing a long README file where you could just write like 10 lines of Docker file so I can reproducibly build the image, but that was not possible. Anyway, Erkki has added Spring Boot-based image here. To my surprise as well, there's like now multiple vendors of Java JDKs and images, and I'm like, what is going on? I don't know.
One is open source and one is...
But there was more. There was like at least 4 different versions. There was Eclipse, Amazon, something from Microsoft.
These are just the container images. I don't know why the container images are so unstandardized. I believe that Oracle itself wants money and doesn't just publish the images.
Okay.
And then there are a lot of third parties.
Okay.
Yeah.
So Oracle doesn't provide an image, right? Oracle doesn't provide an image.
Yeah.
They provide a paid image.
And also most of this...
No, because when you look at the Docker Hub, like for example, OpenJDK, it says deprecated or something.
Yeah, exactly.
Yeah.
So like
This is from
deprecation notice. I bet they got sued.
There are some legal restrictions for publishing Java images, so most of them like...
Okay.
You can distribute Java binaries, but not images, something like that.
But this is like an example how you can kill a whole ecosystem. I would say this is. I would say it's terrible that there is no single official Java image. Like what the hell? And now you have like 5 different ones from different vendors. Anyway, so to elaborate what's going on here, so use the Eclipse image because it has more like lots of tooling.
It has the Maven built in.
Ah, right. It has the Maven built in. Maven is like what? NPM.
The package manager, yeah, but it also is the real life. No, it's not a single binary, but it does something with other pipes in other places. So it has to be installed on the system.
Okay.
So
Maven needs to be installed in order to do stuff, and
it's a package manager. Like
Yeah.
any other.
but it does lots of other stuff as well. I think
Huh?
it does other stuff as well.
Yeah.
Yeah. But the structure is the same. Again, copy the dependencies file, run Maven to compile it. But I think this doesn't properly handle the caching, I suppose.
It doesn't.
Yeah.
Yeah. I tried to achieve it, but I'm not.
Yeah,
I'm not the author. Yeah.
And then for the final stage, again, use some sort of smaller base image, copy the build artifacts to the final image, and then run it. So just an example again.
And 300 megabytes.
No, it was quite slim even. I don't remember by head.
I mean, that's what I'm saying. If you use the multi-stage building, then you actually still can get down to reasonable sizes. So let's see how big this is. This was Spring. So it's 200 megabytes. I think this is fine, actually.
In modern world.
And I also have here the fast HTTP. This is a Go library, but I then realized that it doesn't have routing built in, and then the Prometheus metrics do not make sense. Basically, the point is that I would say like the decent web frameworks should have some sort of path to function mapping, so you could group the metrics based on views. But fast HTTP just doesn't do any routing, so metrics become pretty much useless because you can just make a bunch of random URL requests to the pod, and you can just fill it up with random garbage. I think that's not reasonable. And I also have here Flask, which, okay, is it cloud native? I don't know, but this is like a way to run Flask if you want to. With Flask, I'm doing yes, what I already showed in the slides. And the fast HTTP Docker file is exactly the same as it is for the other one. I think fundamentally it's the same stuff. So I would maybe add someday add Ruby, and maybe even something with C++. So I think if you would use a decent framework with C++, and maybe not do like vanilla HTTP, maybe do like gRPC, then it's a reasonable option to use in a as a backend service, maybe something that does some sort of heavy lifting. Talk to it over gRPC. You have some sort of validation of the data that comes and goes. You cannot directly exploit the memory bugs inside the binary. Then I think C++ is a reasonable option as well. By the way, most of Google Infra nowadays is C++ applications.
Already or on its way?
No, it is. It is. Because Google decided to migrate everything to C++ many years ago, before Go was even designed. And one of the reasons why Go was designed was to write admin tooling. So basically, all of admin tooling is based on Go, and all of the production software is based on C++. And well, the outcome is that outside Google, all of the cloud-native production software is written in Go, and admin tooling is written in Python, I think, maybe. Okay, but yeah, okay, I would say, I think nowadays, yes, most cloud-native admin tooling also is written in Go. I think everything is in Go, basically.
Even Docker?
Partially, yes, probably, yeah. But the thing about other thing that I forgot to mention about Docker is that it's just the front end, and Docker. There's this Docker Mobi. Basically, this is your. That's when Docker got split up into different pieces, and what you use from the command line is just the front end to the container runtime. So. What we used to know as Docker is now a bunch of like Lego pieces, basically. And Mobi is one of the project names. So I guess, yeah, your question.
Did you have any kind of problems because of size of Docker image, for instance, 2 gigabytes?
No, I mean, the size is not a problem. It's just, okay, if you're asking like, why do I do this? First of all, just to get whatever shipping times lower, so you can get stuff running quicker. And the other aspect is, I mean, it saves some space, but and one other issue I had was that if you're grinding lots of images throughout the day, you might actually use up the disk space on the Kubernetes worker. Like AWS creates the Kubernetes workers with 20 gigabyte disks by default. I have now started to bump it to 50 gigs at least to make sure that you don't run out of disk space. But that's one of the issues.
Oh, and I guess it's the cost provides some additional expenses.
Yeah, of course. I'm not sure how much it would be. Is it measurable or no? Okay, so for the practical practice now, what you can do is that you pick one of your favorite languages, you hit the fork button, you fork the repo under your own GitHub account. And then you need to do one manual step, something that I haven't automated. You log into Harbor, and you log into Drone Code Mowers. So you log into both of these, and you do a very dumb copy-paste. OK, first you need to hit the sync button here. I mean, after you have forked the repo on GitHub, you hit the sync button here. Then it syncs up the stuff that you have on GitHub. So let's say hello Rocket. You see, it sees the one that is under the CodeMowers org, and it also sees my personal one. But the CodeMowers org doesn't have passwords to do anything. So that's why you're supposed to fork the repo, so you would have it under your control. Then you go to this repo on the drone website, and I think if you go there for the first time, it shows something like, let's see, I will disable it for a moment. It shows this, right? This repository is not active. I think it just tells the drone that, OK, start monitoring this repo. And drone, yeah, it will be looking for this .drone YAML file from the repo. Let's look at this file for a moment. So it's looking for this drone YAML file. And that's what I like about drone. All of the pipeline steps are Docker images. So I have only one step in this pipeline. The drone itself will basically figure out the Kubernetes worker where to run this. It will clone the Git repo, and it will start this image in that Git repo. And drone Kaniko will basically just read the Docker file and execute it, and finish up with uploading the Docker image to Harbor. And the thing that you need to manually set up is this Docker username and Docker password secrets. And the way you would set it up is that, oops, not here. In the CodeMowers Harbor, you would do, where is this? Robot accounts. You do a new robot account. You put here drone. Yeah, I already have it. Okay, let's do drone 2. Set it to never expire. And OK, I think you would have only your own projects, right? Mark the project that you want to include under this robot account. It will create a new robot account in Harbor, and then you just need to go. It's very confusing, right? I should have automated this, right? No. So you would go to this Hello Rocket drone project, and then under settings, you've got organization secrets. And under organization secrets, you would create 2 new secrets where you copy-paste the stuff that you got from Harbor. This will basically set up your user in drone to be able to push into your project in Harbor, the Docker registry. So once it finishes building, it manages to push the image. Maybe one day I will automate this, but I didn't have time to do this.
There are 2 sections of secrets, organization and private.
Yes, so that's so the first one is this particular project specific, but if you're dealing with your own organization, you can set it up so all of your GitHub repos.
Like username.
Yes, yes. Your username becomes so
once
everything.
you set organization secrets, they are usable across builds.
Yes, 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 across different projects. Basically, whatever private project you have on GitHub, you can build it on this drone, upload it to the Harbor, and use it.
I am asking because I observed issues with this. Like private personal secrets are working fine, but organizational
Or not? But did you set up the on the Harbor site? Did you select the correct scope for this secret? Because there's you can configure lots of stuff here. But yeah, I will need to automate this because it gets people confused. So And the outcome is that any Git repo that you have on your GitHub account, you can activate it in here, but you're supposed to have the drone pipeline description there, which you can just copy paste. This is a copy pastable file, and you hit the new build, and then it starts doing stuff. And so it will first clone the Git repo. This will be happening now actually in the cluster. Let's find it. Where is it? I have very ugly setup here. It gets everything is in the default namespace. Ah, yeah, a new pod appeared, and then it's got all this drone messy, like all of the parameters get exported to this pod and whatever. So it managed to clone the repo, and now it's building the image.
Can I use it as an alternative for the CI to run tests before?
Yeah, but then you would need to describe it in the pipeline somehow. So, so you would have additional steps here, and then you would need a Docker image for the test. But that's the beauty of it. Yes, I know that phase. I also had that phase, but you just need to grind it enough until it makes sense, and it makes perfect sense because all of the CI/CD pipelines, they become so simple. Everything is a Docker image. Your test is a Docker image. Everything is Docker image. That's what I'm saying. You do not have plugins as such in the CI/CD pipeline. You just have Docker images which get run inside the pipeline. But I know that emotion. I had the same emotion like 2 years ago. I was like, what? Why? Can't I just run a shell script? No. You can. What you can do with a shell script is that you can package it up as a Docker image, for example. So it's nearly okay. This Rust project will take some time because it will now it's now downloading the dependencies and then la la la. But basically, the outcome of this is that you will have your production image in the Docker registry. And again, to clarify, drone is the what is it? CI tool. You use it to build images, but you can also you can run tests there as well as the pipeline elements. But I mean,
it makes sense to squeeze tests into.
Yes, of course it does. But I'm just saying that the test itself should be a Docker image. I don't know how you need to figure it out for yourself. How do you formally put it down? But like for example, let's see, for a Python project, how would it be for a Python project? You would have in the source code repo, you would have something like, in the source code repo, you would have something like this PyTest. So you need something where you can run PyTest. So you would likely do some sort of, okay, maybe a dumb scenario here. You would have a step that has an image PyTest. Maybe there is a readily available PyTest image. And then, yes, and it will run the test against your source code because the source code itself will be placed under like /drone or something like that. You need to look into in the manual where it puts the source code. But basically, like the way the drone works is that it will do the git clone for you into a blank container. It gets placed under like /drone, and then it mounts the same folder into the other containers that get executed step by step. You can imagine it as if it was a pod with a bunch of init containers running in sequence. So you always get blank file system, you always get the very first step, which is git clone, and then all of the other containers get executed on top of the same files. And this drone Kaniko is just an image that essentially does the equivalent of Docker build and Docker push, and it pushes it into this registry. But you see, life gets much simpler when you think about everything in terms of Docker containers. Okay, let me give you some more crazy examples. So any embedded engineers here? You do embedded stuff, right? So I also thought, like, can I apply this to my whatever other projects? Yes, I can. So this is the firmware for the access points that runs in the hackerspace. Totally, again, totally different scenario. Starts off with a Git repo. There's a build step. And of course, that's the one that is buggy. That's where the logging is broken. Build step, actually, let's see what it uses. So it is a drone pipeline. I use OpenWRT as the software on the access points. Turns out, I totally randomly found this, but OpenWRT publishes the image builder as a Docker image. So OpenWRT image builder is the piece of software that produces the firmware image that you can upload to an embedded device. And this gets invoked inside the drone pipeline because it's a Docker image. You set the environment for this container, like wireless password, all the packages that go inside the image, which kind of profile to use. So that's where the OpenWRT has different hardware models described, what Wi-Fi drivers it needs, whatever, blah. Installs a bunch of packages. And right, what I forgot to mention, once you have this image pulled into the pipeline step, you can start commands inside that container. So it will copy the file system overlay, which has like config files. It will create some directories. It will set some variables, blah, 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 blah. And this is actually make step. So this is the step that actually invokes the OpenWRT building step inside the container. And it will place the binary at a predictable path. And the second step is there's an image for sending email. It will send the firmware image to me over the email because it contains the wireless password. So it's not pushed into some website where you can download it, but it just sends it to me so I can flash it to the access points. But this is just an example which still very heavily uses containers, but the outcome has nothing to do with cloud or containers or anything. But just to mess with your head a bit, that yes, you can use Docker image to build firmware for an embedded device. I also did something similar for the pizza is cooling down, right? Everybody's getting pissed off, so we need to wrap up quickly. So the ESP8266, I got so pissed off at having to compile this. I tried to compile this toolchain on Ubuntu several times. I got so mad tracing down these dependencies, like on new Ubuntu, it needs some different version of the library. I got so pissed off that I just said, "Fuck it, I'm gonna make a Docker image for this." This now, of course, doesn't have actually anything to do with the drone, but just the fact that I can reliably build the compiler for this hardware, I think this is just awesome. And again, how would you invoke this? You invoke it like this. So the binary, the Docker image is hosted on Harbor Kspace's Harbor registry. You have this voodoo here, which basically mounts the current folder into the container so you can run it. So, and it completely decouples the toolchain from your host operating system, which I think is fabulous. Then I can update my Ubuntu without having to worry that, this compiler depends on like 2018 version of Ubuntu because the guys haven't updated some random dependencies. So I think this is really awesome about containers and Docker in general. Okay, I've wasted 2 hours of your life, so I hope you learned something, and let's get some pizza. Any questions? Is there any questions on YouTube?
No, there's some praise.
What?
Spectacularly, it's beautiful how Lauri gives a lot of concise background at just the right time. It's a masterpiece. So yeah, no questions so far.
Okay, let's wrap up. Okay, bye bye. Bye bye, YouTube.